Hello again, and here we are with the third paper in the session that comes from Korea, Multimodal Surprise Adequacy Analysis of Inputs for Natural Language Processing DNN Models. Sea and Shin, both authors, are here with me on the stage, and Sea, I leave to you the floor for presenting your work, please.
Okay. Hello, everyone. My name is Seo that she just introduced me, and I'm from KAIST in South Korea. So today, I'm going to present my work, Multimodal Surprise Adequacy Analysis of Inputs for Natural Language Processing DNN Models. And this work is done with my advisor, Shin. So as we all know, deep neural networks are rapidly adopted in various domains of our daily lives. And applications of DNNs to especially safety critical areas is adding urgency to the need of developing effective testing techniques. Among many studies on deep learning testing, there are attempts to bring some inspirations for deep learning testing in terms of code coverage. As code coverage for detecting a fault in traditional programming, we define a model behaviors as an activation rate of an input and try to find the input which reveals unexpected behavior of the model. We call this as test adequacy, and there are several researches on this, like neuron coverage or K-multisection neuron coverage or surprise adequacy, which we mainly handle on this paper. In terms of surprise adequacy, the set of neurons who represents the model behavior are called as activation traces, in short AT. ATs are usually a dump of neural layer during its execution by an input. So to obtain surprise adequacy, we need to collect AT vector for every input. Under the assumption that activation traces represent the inputs, we obtain a set of activation trace vectors from training data and an AT vector from a new unseen input. Then we measure how much the new AT is from the distribution of training data. So if the input is more out of the distribution, in other words, surprising, the model is more likely to produce an incorrect output. In large, there exist 3 ways to measure this oddness. The first is likelihood-based assay, in short LSA. LSA performs kernel density estimation over the training data and computes the probability density of a new input. The other one is Mahalanobis distance-based, which is called MDSA, which measures the distance between the distribution of training data AT vectors and a new AT vector. The last one is distance-based assay, which calculates the Euclidean distance based on the class boundary learned during the training process. Since all these calculation utilizes the class boundary, it is only applicable for classification models. For all the 3 assay types, a higher value indicates more surpriseness. So we visualized AT vectors from 2 different DNN models. The left side are taken from Resonant Image Classifier trained with CFAR10 dataset. And AT vectors of the right side are taken from the model called SLSTM, which is a graph LSTM-based model for named entity recognition task. The color represents the class labels it corresponds to. And so we can clearly see that each class of resonance, which is on the left side, are unimodal and they're distant to each other. But on the other hand, ATs from the LSTM are in multimodal distribution. Just in case, I would like to clarify the term multimodal in terms, multimodal is used to refer distributions with more than one mode, and it does not mean multiple data domains. Previous work on test adequacy of deep learning have shown meaningful results on images. Surprise adequacy successfully prioritized difficult images, and neuron coverage have generated a new adversarial input. But most of their focus is on image-targeted tests, and research on other domains has been insufficient. But the multimodal distribution of natural language input implies that when testing a natural language processing model, we need to consider its inherent differences from images. Words in natural languages are more discrete, that each token conveys different meanings. And also, semantic meanings of words are also highly contextual, so that not by the word itself, but also its relative position affects the meaning. Also, the length of the natural language input is inherently variable. So here we argue that we need a different ways for measuring the out-of-distributionness of natural language input. In this paper, we would like to expand the scope of deep learning testing techniques to natural language-based tasks. Despite its differences from images, we want to show the feasibility of applying SA for 3 different NLP tasks: text classification, named entity recognition, which labels named entity to each token of the sentence, and lastly, question answering task, which finds the answer span for the given context and question. Regarding the inerrancy of NLP models, we propose 2 multimodal variants of 2 existing SA, LSA, and MDSA, and designed a customized AT extraction method for each NLP task at hand. And lastly, we conducted a large-scale empirical evaluation of our new multimodal SA metrics using 9 different DNN models trained for 3 different NLP tasks. As we previously have seen, ATs extracted from NLP tasks are multimodal. However, current surprise adequacy does not consider these multimodal nature. For example, the existing MDSA assumes unimodal distributions. So an AT that is actually very close to one of the modes, it can be assigned relatively higher distance from the unimodal decentrate. And as a result, this may adversely affect the SA analysis. So here we suggest to vary existing SA metrics to identify different centroids and measure the distance or similarity to one of them. Instead of using kernel density estimation of LSA, MLSA uses Gaussian mixture model to represent the multimodal distribution of ATs from the training data. GMM is a clustering algorithm in which each cluster is modeled as Gaussian distribution. We train the AT vectors of the training data by GMM and represent the membership of each AT vector to the clusters using a mixture of Gaussian densities. And we should note that the K at here is decided by silhouette index, which measures how similar an input is to its own cluster compared to other clusters. Also, original MDSA, it utilizes the Mahalanobis distance considering unimodal situation. For the multimodal version of MDSA, we called MMDSA, we first apply k-means clustering. Subsequently, we calculate the Mahalanobis distance between the input AT and the centroid of the closest cluster, using the mean values and the covariance metrics obtained from that cluster. The following challenge is handling the variability of natural language inputs. Let's say that the DNN model is going to receive the sentence, which is, she sells apple on the beach. Then the model will probably yield 6 AT vectors with the dimension size D. If we extract a sequence level AT by taking average over the dimension given by the DNN model, the rich information among the token level differences may be blurred. So as a solution, we take NER tests as a collection of smaller classification tests. While inputs for NER are given as sentences, we analyze test adequacy at token level. For question answering, instead of taking ATs for all tokens in the answer span, we simply concatenate ATs of the beginning and the end of the answer span. We suppose that the internal representation for answer span will convey the essence of QA model behavior. We didn't consider classification models because they are able to receive a single AT vector. We conducted an empirical evaluation with 2 research questions to show the effectiveness of unimodal assay and multimodal assay. Both research questions performed a correlation analysis between assay and active learning metrics and the model performance. So I'll talk about the active learning metrics later on. First, the evaluation subjects are 9 DNN models, which are all opened in public. We have chosen authorized dataset for each task. And for first, text classification dataset includes sentiment and topic labeling and evaluated by accuracy. NER models are given more than 20,000 English sentences and evaluated by F1 score. We use SQUAD for QA models, and it is evaluated whether the answer span is exactly being matched with the ground truth or by F1 score. Because of the time limit, but I think I have to skip on the details of the models. Active learning is one of the techniques to elevate the high cost of labeling large sets of data. So it iteratively requests labeling a small set of new input and include them to the training set until it meets its stopping criteria. The reason why we talk about active learning all of a sudden is because active learning and surprise adequacy have something in common. They both include techniques that prioritize unseen inputs in order of their difficulty from perspective of the model. Since other existing testing metrics are given by are measuring by the whole set of test inputs, so that's why we're choosing active learning metrics in our paper. So as we can see, we use 4 active learning metrics as a baseline of our evaluation. But I think due to the time limit also, I think we need to please refer to the paper for detailed information on each metrics. To evaluate DNN models with aforementioned research questions, we sorted the test inputs according to surprise adequacy and active learning metrics in ascending and descending order respectively. Following the sorted order, we took the first 100, 250, and 500, 750, and multiples of thousands inputs and evaluate the model by the ordered inputs. So this is the result of it. Inputs in descending order, which is high assay values, are more surprising inputs to the model. And they show poor performance than inputs with lower assay, the red lines. We can observe the same tendency in active learning metrics. And this trend tells us that unimodal assays are feasible to prioritize incorrect answers of classification models. But for other 2 tasks, assay values showed a suboptimal result. But still, in case of DSA, it shows the most effective prioritization results on NER models. For NER models, the multimodal variants showed an improved behavior compared to their unimodal counterparts. For example, MLSA distinguished OD inputs for the other tag with SLSCM. We can see LSA and MLSA on the figure A, or in the figure E, onto its cross accuracy lines. It means that the new metrics can accurately prioritize tokens that will be mislabeled by the model. In contrast to NER models, we can observe that the QA models, especially BIDF and its variants, DocQA and QANet, are challenging to assay analysis. However, there are notably suboptimal behavior from unimodal assay metrics for these models. For example, with the DocQA model, inputs with high LSA values can actually show higher exact match scores than inputs with low LSA values. And MLSA eases this issue. The same thing goes with MMDSA for BIDF. So today, we presented a feasibility study for applying SA metric on natural language processing tasks. So first, we reported that the distribution of some NLP tasks are multimodal, and we proposed that and investigated whether multimodal variants on SA can improve the accuracy of this analysis. So we showed that especially NER tagging, the new metrics can accurately prioritize mislabeled tokens. So this is the end of my talk, and thank you all for listening.
A very nice presentation. I clap for the audience every time.
Thank you.
And we have time for discussing with Sea and Shin. Both authors are here to answer questions. And while the audience warms up, I have one question, because I am familiar with the software test prioritization, but for standard software application. I know this surprise analysis a little, but I am wondering, so your evaluation is about the effectiveness, that is promising. I wonder about the efficiency also. So how much time and resources are needed to apply this prioritization? Is it feasible? Is it overwhelming?
Well, it depends on which model we are targeting on testing, but in case of DSA, which requires calculating the Euclidean distance from the closest input of which is labeled on the different class, its cost is most expensive. But in case of other SA types, it is quite cheaper than those two. And for all of and also for the active learning metrics, we haven't presented on our paper, but in case of variation ratio, it is quite expensive than our other SA metrics is.
Okay.
If I can add just a little bit, the primary cost is the cost of collecting the activation traces for each individual input. But even then, the main cost is actually feed forwarding the input through the deep neural network and then dumping the values from one particular layer. So we're not really looking at something very complicated. If anything, the cost is based on the large scale of the training data set, I would say.
Yeah, because it's always a matter of scale. Yeah. Okay, and of course, when you speak about recognizing natural language processing, you refer to English sentences.
Yes.
And have you made also experimentation, for instance, with your language that is quite different, or?
Yeah, we had an idea about it, especially in case of machine translation tasks might be a best target for our testing, but we haven't found a best NLP model which we can extract the AT vectors which we want. So we haven't tried it yet, but probably as a future work we might try about that.
Yeah, no, because I was thinking that it can change. It can change quite a lot, no? Going from a language like English to a language like Korean or other kind of language.
I'm sure it's probably similar with Italian, but outside English, it is quite difficult to find really large-scale, good quality corpus. So our colleagues at KAIST is currently working on developing a large data set for Korean language. But in fact, I think analysis like this can be useful when we are building up the corpus, because it will allow you to see the biggest sort of weaknesses in the model that you're developing with the corpus. So maybe we will have a chance to actually look at other languages with that focus.
Yes. Everything was clear from the audience. There are no questions. I have shared this session and I was observing that it is covering really a very nice range sample of application of software testing. So the first paper was on mobile, the second one was in images, and in this presentation you started saying that from images you go to natural language. So really thanks for to the program co-chair and the program committee for choosing such an interesting sample of work that is covering software testing in all its range of application. Okay. So if there are not other questions, we can wait from the audience. There are clapping that go ahead. We can also feel and make some discussion. Javier, thank you for the great presentation. I also joined Javier. It was very, very nice presentation. Sea, what are you doing PhD with Shin? Is your PhD thesis?
It was extension of my PhD thesis, and actually currently I am graduated from KAIST, so I'm on working.
Master thesis. I need to correct her.
Master thesis.
She's excited.
I didn't. Okay, so if you are saying that you are almost there and you will be looking for a job, I think you have a good window here.
Thank you.
Okay. Another question that I am curious. I know is a bit outside your work, but so you are dealing with the written text, right? Or you are also working with the voice recognition?
I'm only working on the written text.
Okay. Okay. And by the way, I have been greeting everyone today, saying good morning, but I forgot for you it's good evening actually, because we are covering worldwide. So it's for us is lunch time now, and for you is dinner time.
Yes, I already had my dinner.
Okay, so thank you for the presentation. And if there are not questions, we could also decide to close a little bit in advance and go faster to our lunch or dinner, depending on the geographical provenience. And I recommend all to be here. For you will be after dinner, maybe a bit late, but I would like to invite everyone to the next session that continue exploring testing on specific domain with Alejandra, that will share again a set of 3 papers. Thank you all. Thank you from the audience. Thank you from Alejandra, from Maria José, from Breno, from everyone. Okay. Thank you. So we leave the room, and very good luck for your graduation, Sea. And see you later. Bye bye.
Yeah, bye.